Hello, my name is Milton Montero, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. So the most successful, or one of the most successful models of behavioral data in human decision-making is the drift diffusion model. And the way this model is used in practice is that we take pre-recorded behavioral data from human participants performing some psychological experiment, and we fit the parameters of the model to that behavioral data. And this approach has been really successful at explaining a wide range of phenomena in the decision-making and reaction time literature. However, the model does raise some interesting questions because by fitting the parameters to the behavioral data itself, the model is telling us what these parameters should be to match the data, but it does not tell us how these parameters causally depend on the input stimuli that we've seen or that subjects have been exposed to, and the way that the brain processes that information into a decision. So in this work, we would like to start addressing how can we do this processing from the input itself and get and match the results from reaction time literature. In essence, we want to know how does a raw input stimuli is processed into evidence that can be integrated. So how does the drift in the drift diffusion model arise from the input? And potentially also explain where does the variance in the decision come from? Like what is what's the source of the diffusion parameter? And there has been some research into this topic, mainly, but like Phil Smith in 1995, but this has mainly been for Gabor patches, like simple input stimuli. And we would like some solution that is potentially applicable to a wide range of naturalistic stimuli. Now, before we dive into the details of the model, a good question is, well, we're going to implement some form of perceptual front end, right? And we want to know what assumptions should such a framework, such a model follow. The first assumption that we will have is that posterior inference is perception is a problem of posterior inference over some generative factors. So for example, when you see an input stimuli, raw input stimuli, your brain infers the shape, the color, like these high level, more abstract properties of the stimuli. And we can use that information to make decisions afterwards. Additionally, we should be able to sample from this representation so as to generate evidence in favor of the different decisions that we have at our disposal. Now, we could implement this model in a variety of ways. For the purposes of the present work, we will use recent advances in unsupervised generative models from the deep learning literature. The reason why is that this approach is rather simple as far as deep learning models go, and they allow us to perform unsupervised learning on stimuli that was thought to be too complex or too hard for previous models. So we have some potential to apply it to really more interesting stimuli sets. Okay, so this particular model we're going to use is called a variational autoencoder. And to understand how this model works, we'll start with the idea of a general autoencoder. Now, in this model, the idea is that you take some raw input, you project it through some neural network into some latent space, Z, and then take that latent representation and try to decode it back into raw input space. And we can minimize the reconstruction loss between the two. The idea being that by doing this latent representation Z will try to preserve as much information as it can that's relevant into reconstructing the input, and the capacity of like the size, the dimensionality of this representation will influence how much it can capture from the input stimuli itself. Now, in the case of a variational autoencoder, this representation is not deterministic. It's parameterized by some probability distribution. And the simplest one, the one that's usually used, is a Gaussian, a multivariate Gaussian. So the idea is that we'll generate this latent representation, we will sample from it, and we will generate and we'll decode these samples back into input space and try to minimize the loss. Now, because this is a probabilistic representation, we also introduce a regularization parameter term to our loss. So we will try to make this posterior here Q, which is parameterized by these parameters here, as to match as close as possible some prior distribution. And traditionally, this is a standard normal distribution. Now, once we train this in an unsupervised way, we can actually just take the inference network, generate samples from it, and make decisions with them. So we can use some function to project them into decision space and train these, like for example, if it's a binary decision, we can train it with cross entropy and make these decisions to be as close as possible to the true one, to the correct one. So once we've taken these, and it can be shown that these decisions for binary decisions, these values, these probabilities, or the log of these probabilities is the same as performing a likelihood ratio test. And this means that by integrating decisions for several samples, we're actually performing a sequential probability ratio test. So an approach such as this one allows us to perform an SPRT end-to-end, from input to decision, and train the model to perform it as best as it can. Now, the interesting approach of such a framework is that in the end, we are not constrained to a particular type of encoder, decoder, or latent variable. So we can use whatever, we can vary these architectures in whatever way we want to see if they match or don't some particular behavioral experiment that we've done. And we can also use more naturalistic input stimuli. We could even use videos potentially. Okay, so this is the model that we're going to use. So to test it, we're going to use a very, very simple stimuli set consisting of upside down and upright T's, which is the decision that the model must make. And we're going to manipulate the stimuli in different ways by changing the contrast or and adding noise and with different intensities. Okay, so this is basically to understand a bit what the model does to solve the task. Let's say we have a model that's fully trained, and this is an example image. They're really noisy from a test set, and they're really noisy. A model should be confused about it. And what the generative model does is that it projects this input into latent space. So here you have the distributions. This is latent variable, the value of the latent variable, which is only one, because very simple problem. And this is the probability distribution for upright T's and upside down T's. And you can see that it's indeed a Gaussian. And because it's really noisy, there is a lot of overlap between the two distributions, which is sensible. It's what we would expect. And we can also see what the model is doing, right? The model is basically learning a template. This is the weights of the input weights on the image for each pixel, for each input pixel. And we can see that the model is basically learning a template of the arms of the T's, which is the only thing that's varying because the vertical bar doesn't change. And the model is learning to fixate on those, and we can see where the errors are coming from. When we add noise to these patches here, these get activated when they should. And that's what creates this uncertainty. Now, we can take samples from this representation, and we can see here some samples from the model, and so here now is the value in latent space. These are different samples. You can see how performing an SPRT will create some uncertainty. There's uncertainty in the SPRT because some samples are on the wrong side of the midpoint here of the decision boundary. And we can also see what the model believes each of these samples are. So for example, this one here is really close to the boundary, and it's a very ambiguous T. It has both arms. However, these ones over here are clearer. They're far away. The model is pretty confident that this is an upside down T. Okay, so the model seems to be doing something sensible. What happens to reaction times? Okay, so as you can see here, these are the reaction time distributions for correct and error responses. And unsurprisingly, because we're doing an SPRT, the model does exhibit, like the reaction times from the model exhibit a characteristic exponential Gaussian distribution for both correct and error responses. And again, expected, but it's nice to see that the model can reproduce at least the basic results. Like if it can't do this, there's no point in going on. Additionally, the model does, if we vary, this is done for a noise level of 0.7, so 0.7 variance in the noise. And we can see that varying the noise from really noisy here at 1 to 0 creates this nice monotonic relation in the reaction time for both correct and error responses. So as we diminish the noise, the reaction times go down as we would expect. Okay, so we've talked about how mean reaction times and how drift is being generated by sampling from this representation, and how the amount of noise can influence the reaction times in what seems to be plausible ways. But what about the noise? What about the noise itself, the variability? Okay, so as you might recall, the loss that we're minimizing we're trying to optimize is this reconstruction loss by this prior regularization. And the way we implement this prior regularization is we have a KL divergence between this posterior here and the standard normal prior. Now, we can vary the amount of regularization, so we can tell how much the model should focus on regularizing and approximating the prior or not. And so by varying this in different ways, we will get different posterior distributions. So for example, let's say we have a prior here, standard normal distribution, and now we fit a model that's weakly regularized. So in this case, the beta value here goes to 0. The model only tries to reconstruct. And what happens is that the variance here of the posterior will be really narrow, and the mean will tend to go far away from the center. And actually will go the clearer the image, the further apart it will be. And but now if we use a strong regularization, for example, beta equal 1, which is what machine learning, what the value usually used in machine learning, the posterior will be closer to the center. And so here we will get a lot, and the variance will try to match the variance of the prior. So there will be a lot more variability in the samples, and you can already see where we're going with this, because here you can see that there's a lot of probability mass that's crossing the midpoint. And indeed, if we train a model with weak regularization, so close to 0, this is what happens. So we can see that for these three different input stimuli, we get samples that are in a very narrow range, and they're pretty, there's not a lot of overlap from samples in the same class, and there's absolutely no overlap for samples in different classes. However, if we use a strong regularization, this changes. Like the model is forced to cluster this is the same input stimuli, by the way. The model is now forced to cluster these input stimuli together, and there's a lot of overlap between them, and there's a significant overlap across the two classes. And if we now go to reaction times, what happens in the first example is that there's not a lot of variability, almost none, in the reaction times, and the model can basically infer make a decision with 1 or maybe 2 samples if we add some starting point variability. However, in the case where we have a strong regularization, then there's more variance in the samples. And now the model, well, it needs to take more samples to be sure about its decision. So even for the same stimuli, you would probably get difference in reaction times, which is, again, something that we would expect. So the prior regularization constraint is important in getting variability. Okay, so to conclude, we can generate predictions using the model, and these are related to how we train them. So in essence, models that are trained on harder conditions will gather information faster when tested on the same condition. And models that were trained on lower intertrial variability will react at the same speed, but will commit more errors than the ones trained on higher intertrial variability. And these are predictions that we can later test on humans. We haven't done so because of, COVID. Okay, so to conclude, we have proposed a perceptual front end that allows us to give an end-to-end account of decision making, and explained how different parameters from the drift diffusion model might arise. And we have shown how we can do predictions, generate predictions so that we can later test. I would like to finish by thanking my co-authors and welcome your questions during the Q&A.